Okay, well, welcome to the first of 3 videos trying to teach you how to do volume through calculus. So this is section 7.3, and let me, by the way, I've been filming this and my computer's been slowing down. If that happens, I may stop it and pick up where I finished, because I was about 10 minutes in and it stopped. So I may end up posting 2 videos. I'm just warning you if I have the same problem. I don't know if my computer is having trouble buffering or loading or whatever. But let's talk about volumes. Before we do that, we need to talk about areas. So let me do a little review here. If I had these 2 functions, let me make that a little bigger so we can see it a little bit nicer. If I had 2 functions like this is A and this is B, and I said find the area between there. You guys should know that you're going to find that length, and let's say this is a y2 and this is y1, and we would then integrate from B to A, or from A to B, y2 minus y1 dx. Okay, now it probably has not occurred to you, but area is always length times width. This function is actually a length function. That's a value of length depending upon what x is. In other words, if y2 is 5 and y1 is 1, then this is 4 between here. In other words, this equation is really a length times what? Well, dx, but dx is actually this infinitesimally small slice of that section. And so what is happening is we are calculating this where we use this as a function and this as dx. Now remember, dx comes from delta x, which means change in x. We're taking little tiny rectangles here. I've exaggerated it, but little rectangles. What's the length? What's the width? Make the width infinitely small, and we have our area. Now when we go to a volume is length times height times width. I know we normally don't do it that way. And that, of course, would be the volume of a box, length times height times a width. This is my length. This would be the height, and this would be the width right here. And so we have to have a third dimension. So let me show you something. I have here something that I had out that many of you saw, some of you wondered about. We hadn't quite gotten to it. This, I'll try and show it to you on both sides. This is a function, kind of makes a big slug. It was actually a sine of the square root of x, I think. The function goes, if I hold it up here, I have to be careful or it's going to tip over, kind of goes like this. And what we've done is we've made a volume. And we made a volume by taking semicircles and extending them up from where our graph would have been. We call that the xy plane. They're perpendicular to the xy plane. You're going to see that a lot in your homework. XY plane is your graph. Perpendicular would be up from the graph. On mine, perpendicular would be out from the whiteboard toward the classroom. Now, let me take and show you how we would find the volume of that. So let's say that's our top function. This is the bottom function. This is A, and this is B. And what I want to do is put semicircles in here. Now, this can be hard for you to really follow well. It'd be easier if we were in class. That's supposed to be a semicircle. I know it doesn't quite look like it because I'm trying to make it look like it's coming out of the board. But imagine that this was the semicircle, and I turn that and I come up here. That's what I'm trying to draw. And I know that's a little hard to see, but that is the semicircle that comes out from the board. What's going to happen is I could put, although this has a pretty wide width to it, as you can see, imagine that this was infinitely small. What would the volume of that infinitely small circle, half circle, be? Well, what I really want is an area times dx. In fact, the equation for volume is from A to B the area of our shape times dx. In fact, what I'm teaching you is called areas, volumes, part A of known cross-section. Cross-section would be the shape of it. So if I asked, and I'm going to, what's the area of that half circle or semicircle? Well, the area of a circle is pi r squared, so this is 1/2 pi r squared. Which leads to another question, well then what is r? And r in this case, the diameter is y2 minus y1, so the radius would be y2 minus y1 over 2. And therefore, the volume here, the area then, I should finish this up, the area then is going to be 1/2 pi times y2 minus y1 over 2 squared. As you move across, the length drops from 0, where you'd have no volume, all the way up to back to 0 and all the points in between. And our area, volume then, would be, for this one, from B to A, 1/2 pi times y2 minus y1 over 2 squared dx. Of course, this could all be combined together. I could do 1/8 pi y2 minus y1 squared dx. And I would put that on the outside from A to B. By the way, a lot of times they will leave the pi in the answer. You'll see that. Okay. Well, once you have that basic idea down, it turns out you could put different things in here. So for instance, let's say I said, I'm going to, instead of doing semicircles, I'm going to do squares. So I'm going to take this Post-it note and imagine that that was right there instead. That would be coming out from the board as a square. I'm turning it that way. I wish you could see it from the side, but I can't really do that. I've tried it. It doesn't work well. So imagine that we have the exact same problem. Watch how similar they're going to be. In fact, this one will be easier. I've got my same shape, y2, y1, and I'm going to put a square in here. So it's going to come out from the board. This is coming out from the board. What's the area of a square? Well, obviously it's side squared. Well, what's the side? That's the side. Side is y2 minus y1. And therefore, the area is going to be from B to A, y2 minus y1 squared dx.